Hello, welcome to Quantum Leap. Today we are going to discuss generating function of Legendre polynomial. So this Lagrangian polynomial uh, theorem is there. So that is to show that Pn of x is the coefficient of x power n in the expansion of 1 minus 2xz plus z square whole power minus 1 divided by 2, the ascending power of z. So we need to show that coefficient of z power and compare ascending power of z, this expansion. So this is our the given function, okay, Lagrangian polynomial 1 minus 2xz plus z square 1 whole power minus 1 divided by 2, or else we can write this one like this, okay. So we know this formula 1 minus x whole power minus n, right? 1 plus nx plus uh, n into n plus 1 divided by 2 factorial x square plus n into n plus 1 n plus 2 divided by 3 factorial x cube and so on. So like that we need to use this formula. We can expand this function, this polynomial function like this, okay. So similar thing. So if you consider this one is a x, 1 divided by 2 is n, then we can expand our equation like this, okay. So here 1 minus, so in place of x we have z into 2x minus z. In place of n we have 1 divided by minus 1 divided by 2 is there. Just simply use this formula and expand this one like this, okay. After expansion, just I rearrange this equation like this one. So this is a similar equation. So here 1 divided by 2 is there. Just I expand, this is 1 divided by, this is 3 divided by 2, right? Like that, just I write 1 divided by 2, 3 divided by 2. And 2 factor also I extend this one, 2 factor, okay, 2 factorial. Is it 2, right? So we need to expand this series like this. So this is our nth term. This is our nth term. So if you carefully observe here, z power n into 2x minus z whole power n. If you put here 1, for example, we can get z power 1, 2x minus z, right? So this is our the nth term equation. So please look at this equation. This equation, right? This is our nth term. Nth term. Now, coefficient of z power n in this equation is. So I want z power n coefficient in this expansion. So I have only z power n coefficients in the nth term only. So this is z power n is there. Already here, 2x minus z whole power n also there. So just expand this one like this. The 2x whole power n. Generally we can write like this. So this is our z power n coefficient of the nth term. Okay. Then you need to find what is the value of this 2x minus z whole power n. This function also there here. So for that, first I'm going to use 2x minus z whole power n. Just I expand this one. So like this. So 2x minus z whole power n. This is also Taylor series, right? So we need to expand this one. 2x minus z whole power n. N c naught 2x whole power n minus, because here minus is there, here plus is there. So we'll get alternate minus, right? So in case here 2, I mean here minus is there, here minus is there, then you will get like this equation, all the plus values. So this is our function. So in front of this function z power n is there. After multiplying z power n, then only you need to compare the what is the z power n coefficient of your nth term. So now I multiply the z power n on both sides, then I'll get the z power n, this expansion, then you will get the what is the z power n coefficient value in this term. Okay, see here. So this is our z power. Now z power n coefficient is into power x power n. Then I extend this one like this. So this is our z power n coefficient value. Then I specify this equation number A. So this is our z power n coefficient value. Z power n coefficient value. Here you clearly observe here this 2 and this is 2 power n. Here 2, 4, 6 is there. So we can write this is a 2 power n like this, right? This one, this 2 power n, this 2 power n get cancelled. The remaining term is this one. It is already there here. Just please go through these proper steps. Step by steps are there. And next, we need to compare z power n coefficient in the uh, next to the nth term. Okay. So z power n. So we have this equation is there right here. This is our equation, main equation. This is our equation, right? So what I will what I'm going to do here, z power n coefficient. Here also I'm comparing z power n coefficient. Here also I'm comparing z power n coefficient. So this is our the next term. So n minus 1 term. In n minus 1 term also, I want to compare z power n coefficient values. Okay. So equation number A is there. Like that, we need to find almost 3 equations. This is our z power n coefficient and 2x minus n minus 1. Okay. So we need to compare z power n coefficient here also. For that, we need to extend this term first. 2x minus z whole power n minus 1. Then multiply this term. So in front of this term, z power n minus 1 is there. Then you compare z power n coefficient. So after multiply z power n minus 1 on both sides, then you will get this equation. Then simplify this one like this NCR formula. So you will get the z power n coefficient in the n minus 1 term. Now just I modified this equation like this. I got the equation number 2. So because of further simplification, I use this one like this. Okay. Actually, here I got this equation. You look at this equation here. This equation is there. So this is our nth equation, right? Minus 1, 3, and 5, and so on to n minus 1. 2 power n minus 1 into 1, 2, 3, and so on n minus 1. N minus 1 into 2x n minus 2. This is our equation number 2. So actually, if you extend like this equation, you will get this. It is 2 into 1, 2 into, I mean, 2, 4, 6 like this, you will get. So if you rearrange this denominator value like this, you will find this value. Okay. Then multiply and divide it by this equation. I mean, this term 2n minus 1 divided by n and n divided by 2n minus 1. So we'll get this equation. So what I'm going to say here, you need to compare z power n coefficient and each and every term. So I got equation number B here. Similarly, if you compare the next term of this is our the next term is there in our expansion series, z power n minus 2, 2x minus z, n minus 2 is there. This term also you need to compare z power n coefficient. For that, first you need to take this one, I mean this value. Okay, similar thing, right? Each and every step we are doing this same process. First you need to take this value, then expand Taylor series function. Is I mean 1 minus n whole power 1 minus x whole power n formula. So like that, if you expand this one also, then multiply this term, then you compare z power n coefficient. Okay, then you'll get the uh, b value, I mean c value. So I got here the almost three equations, a, b, c. So I didn't mention the equation number 1, 2, 3, 4. Equation number a, equation number b, equation number c. So all this information, if you substitute in our equation number 1, this is our expansion series, right? Then you substitute this one value here, equation number 1, so in the term also, then you will get this. This is our z power n term, okay, minus n into x power 1. So after substituting and rearrange this equation, you will get definitely this value. This is our Legendre polynomial. Okay, very important formula this one. So why I am discussing this one, especially when we solve eigenvalues and eigenfunction of Schrodinger equation. Not only eigenvalue and eigenfunction Schrodinger equation, the Schrodinger, I mean hydrogen atom like problem. You want to solve that the polynomial exactly how you got the wave functions. You need to substitute these polynomial functions. These are the similar polynomials. Of course, we are using Hermite polynomial in hydrogen atom, Lagrange polynomial, Hermite polynomial, not exactly Lagrangian polynomial. So if you understand this thing, then you will easily get the Bessel, Hermite, and Lagrange polynomial function. Also, these are all the similar process. So you need to this coefficient z and z square z power cube will be written like this: p1 of x, p2 of x, p3 of x, and so on. Hence, we can write this function like this. So 1 minus 2xz plus z square minus 1 divided by 2, we can write like this. So this is our very important formula. By using this formula, consider this formula, this generating function of Lagrangian polynomial. So we can find many problems. In many national exams, they are asking what is the Pn of x value, P2 of x value, P4 of x values. I observed in many CSIR NET gate problems also. So this is what we're going to remember in formula. So by substituting this value, you will get the many problem answers. You can solve easily by using this generating function of Lagrangian polynomial. So that's all for today. If you like this video, please share and subscribe. Thank you for watching.